Hey guys, welcome back to my channel. How's it going? And in this video, we'll dive into the fundamentals of probability theory. We'll explore how to assign probabilities to events in a sample space and understand the basic principles that govern these assignments. By the end of this video, you will have a clear understanding of how to calculate these probabilities for simple and compound events. Let's start with a simple example. For example, tossing a single die once. We want to find the probability of rolling a 2 or a 5. To solve this, we need to understand the sample space and how probabilities are assigned to different outcomes. So let's understand the sample space in our specific example. A sample space would be denoted as S, as we discussed earlier, is the set of all possible outcomes of an experiment. For our die tossing example, the sample space would be something like the set of 1, 2, 3, 4, 5, and the 6. Each element in this set represents a possible outcome of the die toss. When we assign the probabilities to each outcome in this sample space, we need to ensure that the sum of probabilities equals to 1. This is the fundamental rule in probability theory. If we assume that the die is fair, then each outcome has an equal probability of occurring. Therefore, the probability of each outcome equals to P of 1 will be equal to P of 2, and the same for other outcomes, P of 6, which equals 1 over 6. This uniform assignment of probabilities is a common approach, especially when we have no reason to believe that any outcome is more likely than another. An event is just a subset of a sample space. For example, an event of rolling 2 or 5 can be represented as event A, which is a subset of 2 or 5 can be represented as a set of 2 and 5. To find the probability of this event, we sum the probabilities of the individual outcomes that make up this event. So to find the probability of this event, we just need to sum up the probabilities of possible outcomes, the probability of 2 plus probability of 5, which equals 2 or 6, which equals 1 over 3. This calculation shows that there is 1/3 chance of rolling either 2 or 5 on a fair die. And this is basically the difference between the classical and frequency approach, as we discussed in our previous video. The method we just used in this example is known as the classical approach to probability, which assumes equal probabilities for all outcomes. However, there are other ways to assign the probabilities, such as the frequency approach. The frequency approach relies heavily on empirical data and observed frequencies to determine the probabilities. Both methods are valid, but the choice depends on the context and available information. And of course, in most of the theoretical challenges like this one, we're going to rely on the classical approach. So when we solve just challenges from the textbook, of course, the best course of action is just rely on the classical approach, which in this case implied the equal probabilities for each possible outcome from the sample space here. Understanding how to assign and calculate probabilities is crucial for building mathematical models. These models help us predict and analyze real-world phenomena. However, the success of these models must be tested through scientific experiments, much like the theories in physics or other sciences. So in this video, we've covered the basics of probability, including sample spaces and the assignment of probabilities. We have also worked through simple examples to illustrate these concepts. And in our future videos, we are going to explore more complex probability scenarios like conditional probability and so on. So thank you for watching this video, and I really hope you found this video helpful. If you have any questions or suggestions, please leave them in the comment section below. I'm really glad to hear your thoughts on that, and I really appreciate your feedback. For more technical discussions, please join our Discord community, and you can also connect with me in LinkedIn just for updates on future content or any other discussions. See you in the next episode, and as always, take care.